Okay, here we have an equation written in exponential form. Notice that A is our base. The exponent, which I have just as x, is the input. And y is my output. Now we can use the fact that the exponential and the logarithmic functions are inverses of each other to get the logarithmic form and then be able to switch back and forth, which is helpful when we're trying to solve and evaluate the logarithms. So since they are inverses, our base is going to stay the same. So if I'm going from the exponential to the logarithm, here I have base A as the exponential. I will keep base A for my logarithm. And remember, with inverses, the input and output just get swapped. So for the exponential, if my input is x, then for the logarithm, the output will be x. And here for the exponential, the output was y. So my input for the logarithm will be y, and the output will be x. They just literally swap places. So we can convert back and forth now between the exponential and the logarithmic form, and we can see how that'll help us solve various logarithmic equations and to evaluate the logarithms. So let's say that we have log base 3 of 9. Log base 3 of 9. Notice I don't have it that it equals to anything, but it does equal to something. So I'm just going to say it equals to x. We'll just call it that. Now, right off the bat, it may not be exactly clear what this is equal to, but we can rewrite it in the exponential form to get a better idea. So to rewrite it in the exponential form, remember our base will still be the same, so I have 3. And now my input and my output swap. So the output for the logarithm is x, so the input will be x. And the input for the logarithm is 9, so the output will be 9. And now we have in the equation in exponential form, and we can ask ourselves 3 to what power would give me 9? And the answer is 2. So if I were just wanting to evaluate this logarithm, log base 3 of 9, keeping in mind the exponential form and how these things convert back and forth, I can just simply ask myself, the base raised to what power would be equal to 9? So 3 to what power gives me 9? And the answer is 2. So we've evaluated now that logarithmic expression. So let's do another one. Let's say log base 4 of 1/4. And I want to evaluate this logarithm, log base 4 of 1/4. So keeping in mind the exponential form, we can ask ourselves the question, 4 to what power gives me 1/4? And so we see that it has the same number, it's just flipped upside down, so the reciprocal is taken. Hopefully that jogs a little bit of memory, that it would be -1. And we could come off to the side here and see that 4 to the -1 is in fact equal to 1/4 if we remember our exponent rules. All right, so we can also use converting between the exponential and the logarithmic form, not just to evaluate the logarithms, but to solve some basic logarithmic equations. Before we move on to that, let's look at a couple special bases for the logarithms. Special bases. So with most bases, you're going to see it. Like this has a base of 3, got it. This one has a base of 3, this has a base of 4, but there's some special or common logarithms where the base is just implied, but it's not written out. So one of those is log base 10, and we'll just say of x, log base 10 of x. This is called the common logarithm, and you're never going to see it written this way. When it is a base of 10, we write it just log of x. So when you see log and no base, then we know that this is actually the common logarithm and it has a base of 10. So let's look at evaluating real quick. Log of 0.1. And I want to evaluate this logarithmic expression. So again, I'm going to think the exponential. I don't see a base and it is log, so I know it's a base 10. So 10 to what power would give me 0.1. We could rewrite this expression to be log of 1/10, and it may be a little clearer now. 10 to what power gives me 1/10, and like the last example, it is -1. 10 to the -1 power gives me 1/10. So there is what we call the common logarithm. If it's just log, then we know that's an implied base of 10. The other special base is the natural logarithm. Logarithm, yeah. So these two, the base 10 and the natural log, are going to be the ones you're going to find on most calculators. There are some fancy calculators now that allow you to put in the base, but most of them don't. So the natural logarithm is actually log with a base of e, so log base e of x, if you will. But again, you're never going to see it written that way. This is actually ln of x, the natural log of x. And again, we can simplify some logarithmic expressions with that base. So this is how I write ln. So let's say we have ln of e to the third. So recognizing this is the natural log, I know the base is e, and again I can ask myself, e to what power would be e to the third power? And hopefully we know that would be 3. E to what power gives me e to the third power? It would have to be 3. So now that we know our special bases, let's use everything that we have talked about to solve a couple of logarithmic equations. So we want to solve log base 2 of x equals -3. So just using the exponential form would allow us to solve this. So remember, our base would have to be the same and the input and output are swapped. Something that I like to use when I'm converting back and forth from the logarithmic to the exponential is what I like to call the circle of life. So I'll start with the base, raise it to the power of the output, and that will be equal to the input, so it makes a little circle. So I can rewrite this as 2 to the -3 is equal to x. And now we can see we essentially already solved this equation. I just need to simplify 2 to the -3. 2 to the third power gives me 8. The negative implies I need to take the reciprocal, so I get x is equal to 1/8. And once we learn some of the logarithmic properties, we can solve more complex problems.